Welcome to the session Bytecode pattern matching. While this talk, I also as a title, you can use this title as well. We're going to talk about Java, we're going to talk about Kotlin, about code coverage, and about the best friend Bytecode. There will be some scandals, some intrigues, some investigations. Before we start, usual disclaimer, my employee can only dream that they own my ideas. And yeah, by the way, I work in a company, SonarSource, producing such a great product as a SonarCube. But today we are going to talk about something which is a bit different from SonarCube. For about 10 years, I work on Java code coverage, and we are going to talk about this. Yeah, and so let's do a quick check. Who is writing tests? Okay. Who is measuring code coverage? Okay. Who is using javac library for that? And of course, EclipseCon plugin that does the same. Cool. So, while developing EclipseCon and javac, we do some intensive testing on 7.5 GDK versions. We're going to see quickly why we need to do that. And yeah, out of this testing, sometimes we find bugs, not only in our product, but sometimes in GDK. We report them back, sometimes we contribute the patches. Sometimes we add the new features to the javac library, and then they transitively come to Eclipse plugin, EclipseCon, because EclipseCon is based on javac. So, for example, recently we had such coverage report for some Kotlin classes. By implementing some new features just in javac library, we managed to improve this report. So you don't change the tests, but the report becomes better. And exactly about this we're going to talk today. We're going to see why this happens. And before we talk about that, it's important to understand that javac receives all the information from the class files. So this is pretty neat. It allows to simplify integration of code coverage measurement into the build process. It opens a door for languages other than Java, Kotlin, Groovy, Scala, whatever. And yeah, another quick check. How many people here are interested in a Kotlin? Okay, not that much. So maybe I wouldn't focus more on Kotlin. Maybe we will focus more on Java. Yeah, and absence of source files is not an issue for javac, so you don't have source files. We will anyway manage to measure code coverage, and we'll show you some figures. Of course, you won't be able to see the exact lines coverage because you don't have lines, you don't have source code, but we will show you the measures, how many classes, instructions, methods, etc. were covered. Of course, this helps us cover any new features in newer versions of GDK. For example, if there is a new syntactic sugar and it doesn't affect the bytecode, it's pretty simple for us. We don't need to do, in most cases, we don't need to do anything. Some examples of such features, they include switch expressions, row string literals that are currently integrated into GDK 12 and as a preview feature. So, before we really start, here is a real disclaimer. There will be a little bit blood out of JVM, sorry for that. You can, I think, still open the door and exit. We will look into internals of javac and Kotlin compiler. If we will have time, we will also look at Eclipse compiler. We're going to talk strong language. We're going to talk mostly bytecode. And thanks to that, it wasn't required to translate much from Russian to English because bytecode is an international language. And we don't have much time, so it will be quite intense. I will try to do intense violence of your brain. If you're not ready for that, please leave the room. So, ready? Okay, let's go from Java. Let's take a pretty simple example. Let's take the following empty class, whose name is, by chance, bless me. Who is agrees that this class is empty? Okay, let's do a check. Let's compile it. javac, bless me, pretty simple. Let's decompile it. For the decompilation, we will use the standard GDK decompiler, javapim, -v verbose, -p show privates, etc., etc. So we decompile it. What we see in it, we see, yes, we have a class file. It was compiled from the following source file. It was compiled with javac 8 and targeting Java 8. So it has a major version 52. We can see so-called a constant pool. Constant pool is all the constants used in a class file, so that later instructions, they don't need to repeat the same strings, the same constants over and over again. They just can point on a number in a constant pool. We wouldn't focus on constant pool on later slides. And then what we see that actually this class is not at all empty. We see that there is a default constructor. So here is a default constructor. What it does, you know, every class in Java has a parent except javac object. For all classes except javac object, if they don't extend something, they anyway implicitly extend javac object. So we need to call a constructor of a superclass, and here is an invocation. Of course, every method can't just fall through the body of a method. It should end with something, or abruptly by throwing some exception, or just return from the method. So we also see the return. And we see a little bit connection with the source. We see the line number of some instruction, and we see the source file name. As you can see, source file name is just file name. It has no notion of package or directory or whatever. It's just source file name. And exactly this connection with the source is how Jacoco can show you line numbers, but it's very thin connection. It's important to understand. Well, let's take another simple example. This time we're gonna call our enum really empty without any God bless to make sure that it's really empty. Who agrees that this enum is empty? Okay, this time nobody. Let's check. We compile, we decompile. Again, there's constant pool, but it's not shown. What we see some magical fields appearing, which we don't wrote in our source code. We see a field $values. This field is an array of type of our enum. We will see quickly why so. Also, we can see that it's private static final. Those beasts we know, but also we can see that it's synthetic. What synthetic is, we will see shortly. Remember the word synthetic. We also can see here method values. You all know that on enums you can call the method values, and it's going to return you all the values of your enumeration. And this method exactly returns you this array. So we can make an assumption that this array all the values of the enum. We can see the method value of. It returns enum by a string value. We can see the constructor, as we said before. Every class should have a constructor. And we see a static initializer. This static initializer exactly populates the array. In this case, since our enum was empty, well, the array is empty. Why it's important? Why it's important for tools that work with the bytecode? If such tools are not aware of such a generated code, they will analyze it, and they will show to the user something that user doesn't expect. For example, in Jacoco 079, we were showing, well, you didn't cover it a method's value of, you didn't cover it method values, so please write the tests for those. But it's somehow useless. Let's just trust the compiler. Why do we need to cover those methods? They are compiler generated. Usually compiler doesn't produce a bad bytecode. So let's fix this. Let's implement some filters. Let's remove those methods. And that's exactly what we did. It transitively again came to Eclipse EclEmma. Those methods are filtered out. What we unfortunately forgot is that some people actually use enums as a nice container for static utility methods. So actually constructor also should be filtered out. So we filtered out constructor as well. And for an empty enum, now we can get 100% coverage if we just use the enum. Back to the synthetic. If you open our Bible, which is Java Virtual Machine Specification, we could see in it that every class member that doesn't appear in the source code must be marked with a synthetic attribute. So whenever something appears in the bytecode but does not appear in the source code, it should be synthetic. And there is exception. As in any language, there is always exceptions. So the only exceptions are default constructor that we've seen already, class or interface initialization methods. We've seen initializator, it was not synthetic, and the two methods, enum values and enum value of methods. So that's exactly what we've just seen. Why those constructions cannot be marked as synthetic, whereas they do not appear in the source code? Does anybody know? Super simple. Everything what is marked as synthetic is for sole use by the compiler. Compiler could reference those things, could call them, etc., but the synthetic things, they are not accessible in IDEs. IDE will never show you in after completion something synthetic. And this is not good for enum values and enum value of, and of course for the constructors. They should appear in after completion and so on, and they should be accessible by a user. Boom. So, and then in the same Bible, a little bit later on in another paragraph, we could see that synthetic attribute was introduced back in JDK 1.1 to support nested classes and interfaces. Let's have a look on this. So we have another simple example. We have outer class, inner class, pretty simple. We have private constructor in an inner class, and we invoke this constructor from an outer class. What could happen here? Let's see. Again, we compile, we decompile. Again, Java 8. So here is a constructor invocation. What's interesting here is we invoke constructor with some argument. Our constructor was not accepting any arguments. What is this beast? Let's have a look. Let's have a look on the inner class. Here is our private constructor. It has no arguments. And here is another constructor which was generated, which is synthetic. And this constructor accepts some argument. Why this is done? Because our constructor is private. The new one is package local. This is done because while in Java language specification in another Bible, we have a notion of inner outer. In a virtual machine specification, there is no such notion, or at least was not. And so classes, they actually not nested to each other, they lie next to each other. And to align the rules of the Java language with the rules of a virtual machine, we should provide to the virtual machine an accessible constructor. So here we are, we remove the private, we make it package local, it's synthetic because it's generated, and now virtual machine can actually invoke this one. Yeah, and it simply delegates to our private constructor. So this time, if you look on this a new generated marker class, which appears in the second constructor, we can see that this one is really empty. And this synthetic class is here just to make sure that the signature of one constructor is different from the signature of another constructor. You can't have two methods with the same signature. And yeah, it's synthetic. This changed recently. If you visited yesterday's session about Eclipse Java compiler, you already know that in Java 11 there is nestmates. If we do compile exactly the same example, we could see that there is a significant weight lost. There is no more new constructor generated, and all this possible is because of a new attribute nest host. So now JVM learned how to JVM learned a notion of nesting, and this is pretty cool. Another example is Accessor Methods. Again, if you've been yesterday on Eclipse compiler presentation, you already know that. We have an outer class, it has a private field. We have an inner class, and we increase the field in the inner class. So what happens here is up. Here is our increment, but there is no increment. There is some strange invocation of some method. Let's have a look on what this method is. And this method is actually doing the same trick as with constructor. It's now package local, again for the same reasons. and this method does an increment. They all again changed with Java 11. We have again the lost in wait. We don't need this indirection because we have new attributes. In this case, we have nest members, which describes, okay, I'm an outer and I have following inner classes. And yeah, in the inner class, we now see the new attribute nest host and direct increment here. Because again, JVM knows the relation. Another interesting example you all might know already is a bridge methods. We have classes, one extends another, one overrides another, but they have different signatures. And you know that in Java invocations, taking into account the whole signature, taking into account also the return type, but return type here is different. So in places where as both A and B, because, for example, the argument is just an A, you can pass here B and on the class A, but on the instance, which is actually B, the fun method, and you actually expect to return the object. In implement this, javac again has some interesting trick. We can have a look on it. It generates the synthetic member. This time, member also has an attribute bridge because it bridges communication between two methods, and it's simply, yeah, it's synthetic bridge, and it simply returns our original method. Why this is done? Yeah, well, the places where I expect signature javac object funds, here is the signature, just call it. Bam. Out of all this, we can make, for bytecode manipulation and analysis tools, we can make a simple conclusion. Let's just ignore synthetic. It's not the code that user wrote, right? Right. And we did that. But what about lambdas? We forgot lambdas, so let's have a look what happens with lambdas. We have a simple method. It just calls on run method on a runable. And we pass to this method lambda as an argument. Please notice that we have here, and the string appears, well, it's not shown here, but it appears on line 9. Let's again compile all this, decompile. Here is our method exec, nothing interesting here. Here is our method fun. Where is Joker? There is not Joker, there is no line 9. But here is a synthetic method generated for lambda. This is lambda mechanics. We are not gonna go deep into that, but lambda is implemented in a way that of goes in a new synthetic method. And in this synthetic method, here we can see the Joker, and here we can see line number 9. So if we just ignore all the synthetic methods, we're going to miss the cover of the bodies. And this was exactly the case with all Jack conversion. We need to fix this, so let's ignore all except the lambdas. Well, average. Another interesting case, switch on enum. So pretty simple. We have enum with two values, true, false, why not? And we have a switch by this enum. 3 cases, false, true, default. Let's compile, let's decompile. Here is our method example. What we can see here, switch, nothing special, 3 cases. But also we can see something strange. There is another class which we didn't write. Let's have a look. Static, we didn't write. It holds a field switch map, which is synthetic. What this beast is, let's have a look. It's actually used in this class initializer. And what happens here is that in a switch map, we put a value, the current value, the ordinal value of a constant false, and we associate it is with a value true, we associated it with a constant value 2. Why this is done? If we go back to our switch, we could see that switch happens exactly by the value of this switch map. Why this is needed? Because, well, we could serialize it later with the new values, or, for example, we could compile the enum later on and break after that. The switch shouldn't break after of a new values in enum or after removal of values into enum. So we need a way to associate an old bytecode with a new one, and switch map does exactly this. An interesting thing, if I'm not wrong, Eclipse compiler is a switch map into the original class, not into a separate class. Well, again, why it's important, if you are not aware of that, user will see something strange in their reports, their analysis, they will see something they we need to filter this synthetic class. At this moment of time, you might ask if I have something not synthetic. I don't, but in Java compiler there is. So let's have a look on something non-synthetic. Assertions. Pretty simple construction. We can assert on some value. What happens inside? Inside we again get some magic happening. We have assertions disabled field. We have initializer that populates this field. Why this initializer is needed? Well, because you can specify assertion status. You can disable per class or disable it. And it's pretty complex operation to go to the runtime and ask each time, is my assertions enabled or not? So let's simply cache this value, and this value is cached in a static generated field. And that first, where assertions happens, first we could check whether assertions enabled or not, and only then check the actual assertion code and throw an error. Well, again, what happens here, if bytecode library working with, it will show there is 6 branches, but user didn't write 6 branches. User didn't write this first branch which checks it's enabled or disabled. And well, we still actually open it. Hopefully we will resolve it soon. Let's have a look on another switch. Let's have a look on switch with a string. Simple. Here is a switch. 3 cases. What happens in the bytecode? Well, pretty big bytecode. Let's zoom in. And we can see 2 switches. We had only 1, right? But we got 2. Why? Well, because the first one is a switch by hashcode. It's pretty natural way to implement switch by string because it's pretty efficient. Hashcode is cached in string, so most likely it was already invoked before we came to the switch, or if we came to the switch multiple times, it will be cached. And with pretty good probability, we will, by switching by hashcode, will determine which case we need to pick up. And if it was unlucky, like in this case, those 2 strings, they do actually have the same hashcode. We also need to do a little bit of equals checking to determine whether it's really the case which we expect. So here is 2 comparisons, and the last switch already knows which case to there is 3 cases, 0, 1 default. That's why we get the 2 switches. And yeah, this results in something like this. Well, there is 9 branches, whereas in the source code there is only 3 branches. The user surprise covers those branches, some of those branches. Again, write tests for the compiler generated code. So we need to filter all this out. Exactly this pattern. And fun fact here is that Eclipse compiler generates another pattern. So we need to write the 2 bytecode patterns to distinguish string switch for the 2 compilers. It's ad hoc approach. Of course, if one day Eclipse or Java compiler will decide to implement string switch somehow differently, we will adopt the pattern. Let's move on. Here is another interesting case, Java finally. We have try catch with a finally, super simple one. Let's decompile. Let's have a look what we see here. We have 3 invocations of nop method, but we had only 2, right? Do you agree? Let's come back. Let's count. I see 3 nops, but okay, one is a declaration. There is actually, in the body, there is only 2 nops. To distinguish them, let's add some marker. Let's add a string. Here is a string. Let's get back to the bytecode. In the bytecode, what changed here? Well, now we see that our invocations are different, and we can see that there is still two invocations which are passing argument finally, whereas we wrote just one. Why this happens? Well, this is needed to implement exception. If you know, finally block should be executed on all the passes out of a try-catch block. It should be executed on exceptional case, on exceptional pass. So, for example, what we can see here, exception table says, well, if exception happened in those two instructions, please jump on the exception handler. And in exception handler, we must call a finally block. So here is a finally block and exception handler. And if exception didn't happen, we are not going to go through the exception handler block, but we still need to invoke finally block. So here is invocation block on. Again, we need to handle this. We need to merge those. Users surprised why they have something strange. Well, we do something a little bit more just bytecode pattern matching. We need to really match one instruction on another, and we do this. An interesting fact, a little bit of archaeology. If we will have a look on Java 4, we notice that there is no duplicates. In Java 4, there were pair of instructions. Handling was implemented quite differently. There was instructions GSR and thread, Java subroutine, return from the subroutine. While this in a much smaller bytecode, those instructions, they are not friendly with bytecode. So that's why later on in Java 5 they disappeared and they were replaced by a duplication of a try finally. And by the way, another interesting fact, you know, I hope you know that there is a limit on the size of your methods in the virtual machine. Given that the try finally really duplicates the code, you might imagine what happens if you nest try finally into try finally into try finally. As a homework, try nesting you could have. Let's have a look on another example. We now know how finally is implemented, so probably we try with resources is implemented. Probably there is a hidden finally which closes the resource. So example is super simple. We have a closable resource and we use it in try with resources. Again, we compile, we decompile. What we can see here, bytecode again because of probably duplication, but maybe what we can see there is 4 calls of closable close. Why 4? Well, because we need to make sure that resource is closed. So let's close it 4 times to make sure. What happens here? If you open another Bible, if you open Java language specification, we could see the following statement. The meaning of a statement is given by the translation of the source code. And the source code is actually given. Source code looks like this. We will look at it deeper a little bit later. At this moment of time, we might wonder whether the translation is exactly one-to-one. Basically, what will happen if we will take this source code and will it be exactly the bytecode as for try with resources? Like this. Try with resources, class example, but it uses try with resources. And we have another source file. It's also a class example, but it uses the following code that we've just seen that is copied from the Java language specification. If we compile first one and decompile it and save the result of decompilation into file 1.txt, if we do the same but with a second source file and save it in another file, then we can actually do diff between two, and diff between two is going to show us that the only changed thing between two class files is the line numbers. Well, it's logical. We have lines in two source files. The rest is identical. Let's check that there is actually a bytecode, and well, there is constant pool, there is some bytecode. So indeed, the Java compiler generates exactly the same bytecode in the two cases. You can see that there is a problem for bytecode manipulation tools, because in this case, it's hard to distinguish what was written by the user and what was really generated by the compiler. An interesting fact, Eclipse compiler, let's say, is a little bit smarter. It generates a more optimal bytecode in this case, and quite different one. And the bytecode generated by Eclipse compiler, I didn't manage it. I think it's impossible to write a source code that will compile the bytecode generated by Eclipse compiler. So let's have a look on code. What we see here, we see the try catch, which catches the exception. We see the finally block indeed, as we guessed it. The closing happens in the finally block. In the finally block, in case of exception, and if resource is not null, the resource was opened, close it. While closing it, we need to exception. It happens while we are closing resource. We need to attach it to the primary exception. And if exception didn't happen, well, let's just close the resource, and a new exception will just bubble up. Pretty logical, super simple, but what is interesting, we'll look on those 2 lines. This is a dead compiler can actually prove that resource is not null. We just did a new. It can't be null. It's a dead code. If you look on those instructions, on the path where finally is inlined into the catch, primary exception is never null. So on this path, we also have a dead code. And so yes, users might wonder, report, for example, they might wonder how to reach those branches. Well, they are unreachable because they are dead code. The story is a little bit different if you take javac 9, but still compile into the bytecode version 8. It becomes more smarter. It can avoid some branches exactly because they are unreachable. If we go deeper, if we take javac 11 and still we can compile 8 target, we can see even more smarter. There is no more dead code. This is pretty cool. So again, we need to filter all this out. Well, at this moment, I need to switch to the Kotlin, but there is not much Kotlin, and we don't have that much time, so I will just really step, try to follow. Well, Kotlin data classes, you write a field, you don't write setters, getters. In bytecode, you get a field, setters, no synthetic attributes, because setters should be called from the Java code. You get a constructors, method to string, hash code, equals, etc. All this needs to be filtered out. We filter it. Delegates pattern. We implement some class that will delegate to another class, but some methods we override, some we don't override. The methods that we don't override, well, they anyway needs to be presented in the bytecode. Again, they are not synthetic because, well, Kotlin doesn't need to follow the Java language specification, but also because those methods should be callable by a user. So again, we need to filter them out. We do that. JVM overloads, it's to specify default arguments. In Kotlin, you can use default arguments in order to ease using of default arguments from the Java side when you call the Kotlin code. You can generate multiple methods, one that accepts 0 arguments because 2 are defaults, one that accepts 1 argument, etc., etc. All those also get generated in the bytecode. They delegate to the method that knows about default arguments and initializes them. And again, they need to be filtered. Well, we filter them. Late init. In Kotlin, you know, there is nullable types and non-nullable types. Sometimes it's very convenient to say, well, this field is never nullable, but, well, I promise you I will initialize it a little bit later. In this case, you don't want to make it nullable. You want to really initialize it later, and after initialization, it's always non-null. For example, it's very handy in a test. In a test, you initialize a field in the setup method, then you use it in test method, but you don't really want the field to be nullable. So there is late init. If you have a look on the late init, every access to the late init property results in additional null check, which is generated by compiler. Again, this is not synthetic. There is no way to mark instructions as synthetic, but they need to be filtered out. Well, we filter them out. All the filtering, again, this comes transitively to the Eclipse plugin. Fun fact, IntelliJ idea, so IDE, the same guys who develop Kotlin, it actually are not capable of recognizing these branches, and it actually shows to the users, well, you forget to close this, to cover this branch. There is another interesting construction, unsafe cast. Again, pretty similar to the late init, there is additional null check for safe casts. And well, we need to filter it out. While making presentation, I actually implemented this filter, so it's in master, it soon will be available. Same thing, IntelliJ IDEA shows that there is uncovered branch. When plus enum, you might guess that it's pretty much the same case as for switch on enum in Java. Here's first case, here is second case. Here is switch map, here is first case, here is second case. Well, here is generated first case, which we didn't wrote in the Kotlin, because Kotlin is capable to say, well, you cover it, you wrote in a switch enumeration, so you don't need to default. In this case, Kotlin will generate a third branch, which is, well, one branch matched exception. Why it is here as a protection, you can think either serial, so the branch will be presented here. And again, we need to write a filter for that. We do so. When plus string, we could imagine that it's pretty much the same. It's string hashcode, switch by this string hashcode, and then comparisons. But, well, no, Kotlin compiler generates only one switch. Actually, the same thing does Eclipse compiler. Eclipse compiler doesn't generate like javac two generates only one, and then go to instructions they allow to jump to particular case. So again, we filter all that, IntelliJ not capable, inline in Kotlin, you can mark a function as an, and what happens is that a function will be really inlined in a call site. So here is of the same function. Well, there is a statement that this can actually be mapped back to the place from where it was inlined using GSR45, which is debugging support for other languages. And yes, hopefully it can be, but it's not yet implemented. Well, conclusion. You've seen the source code which you write is not at all the bytecode. So please be aware of that. What you write is not the thing that is going to be executed. In some cases, completely different thing can be executed. Even the bytecode which gets generated is not the thing that is going to be executed. Surprise. Bytecode-based tools have to guess. Be aware of that. So Spotbox, which analyzes bytecode, SonarCube, which analyzes the bytecode, Jacoco, which analyzes the bytecode, they all have to guess in those corner cases where the bytecode doesn't match the source code. And well, we are, and you are, as developers, we have to live with this. So please don't come screaming, there is 20 branches, I didn't write them. Yes, you didn't write them, but they are here in the bytecode. And we are working on bridging the two worlds. And that's it. I don't think that we have any time for questions, but please feel free to catch me after the presentation and ask your questions.